So today I will show how to use the new features in .NET Core and .NET. So this is features that appeared mostly in .NET Core 3.1. And today it's available on .NET 5, on .NET 6. And there are, it has been present for a while, but there were not that much presentation about the topic. So I think it's very interesting to show specifically how to use it and explain the intrinsic of these things. So the idea is here that I had some old video files on my hard drive, which I basically used for display in discotheques 20 years ago. And at that time, all the code to decompress the video was in assembly language. And I wanted to write a new player for these videos. And I was quite confident that it would be hard to do as good as what I did directly in assembly at that time, especially due to the fact that managed language tend to allocate a lot of memory without telling you. And I wanted to try to do something without any memory allocation to be constant memory size in my implementation. And for that, I played with a lot of new constructs from .NET. And this is the result of the thing. And all the things I show here have been also used in production code for part of our system at DH. So this is, okay, a fun implementation of this, but everything has been reused, and even things I did at DH have been re-imported for this presentation in my sample. So the idea is that we have a file which is a flick file or FLH file. And I found the format description on the internet because the internet never forgets. And it was actually files produced by the Animator Pro file format. And at that time, we use it to compress the videos to have a very fast decoding. And as you see, everything is written like file leader, offset, and things like that. And then you have a lot of bytes to read and copy and all that. So this is really the kind of task which is very suited for things like C or assembly, but that we are less comfortable to write efficiently in a higher level language like C# or even F#. So I really wanted to play with this idea and find how we can re-implement this thing like that. So the idea, of course, is that the way we could do is to start with pointers and to play with pointers. And if we start with pointers, we will have code that is where we can do all the memory access in an unsafe way. But the point of managed language is to have some safety. So I wanted to keep part of that and to have something that is safer than what I wrote directly in assembly. And to have also something that is a bit higher level with the safety, more expressive than writing directly C or assembly code. So I will show you the problem with pointers is that when you have a pointer, it will point to a region of memory, but this memory must remain fixed in memory, because if the memory moves, if the data moves, especially due to garbage collector, you will have a problem because your address will point to an old position in memory, but not to where the things are. The problem is that as soon as you want to use pointers inside an array of bytes, for instance, or an array of pixels for the screen, you will have to pin it to be sure that the array doesn't move while you are processing it. And the problem with pinning is that it will make the work of the garbage collector harder, because the garbage collector will not be able to do compaction of the heap if a part of if an object is pinned, because it's mandatory for it not to move. So pinning is good for performance on the execution side, but is bad for the performance of the garbage collector. On the other side, you could also use a plain array, and at this point, you will try to access the arrays through the index syntax. But the problem is that after that, you are contrived to copy your data in an array, and depending on the situation, sometimes it's more, if you can receive data in native memory, you can receive data in a byte array or other arrays, but you will have to write the code for one case or for the others. So you have to make a choice even before knowing where the data will get. You will get the data from, which will have a huge impact on the way you can use it. So since .NET 3.1, .NET Core 3.1, there is a new structure called span, which actually solves this problem. So this is a type called span of t, span of int, for instance, or span of byte. And the idea of this is that your data you can now represent a contiguous region of memory with this type. So here, this is a contiguous memory region of bytes, and the span contains both the start address of this continuous memory and the length. So using both, it can at the same time access the data, and also check that the index is not out of bounds. So it keeps data access safe. Of course, you will tell me, why don't you create a span like creating a type, my span, with an address, which would be an int pointer, like that, int ptr, and the length, which would be an integer, and it would be done. Why do we need to actually create a specific type like span to do this? So it would be, of course, a struct, but here it's not enough, because if I store the address inside inside this pointer, the problem is that with an array, it's still just a pointer. So if you point inside the pointer, inside an array, and the array moves, the span will point to the old address, and then data access will be lost. So it still requires pinning. So what is different inside span from what I wrote here? Actually, we can have a peek at the span.cs code in runtime. And if you look at the code, it's in C#. You can see that it's I will just zoom in the font so that you can see better. Here you can see that actually the pointer is defined with a by reference of t, and then the length. So what is this by reference of t? And the by reference of t here is also a struct with an int win pointer, but if you see here, there is a big warning explaining that actually it's not a real type, it's just a wrapper type, but everything will be managed by the runtime itself. So intrinsic and intrinsic here, everything is intrinsic, and actually the JIT will do some specific when it recognizes this type. So what is this type doing? It's actually saying that it's by reference. What does it mean to be by reference? Actually, the garbage collector has already something for by reference types. Let's show a schema. So when you have a type and it contains some values, some fields, you will have inside. It doesn't. Yes, this is not a good one. Okay, check. So inside you will have some values, for instance, and something you can do in .NET is create a reference variable. So in C# it will be var with an end. So here you have a reference r, which is pointing to this object, and you can do something like r.y with the end, and this will be a reference to R. In F# it's the same way to write it, just with a let like that. And actually this variable will point to the Y field inside R. And then you can do things like assign py with a value, and it will write actually to here. Okay, so this is something that exists in the CLR from the beginning, but the problem with that is that no py is actually an address to this region, and if the object is moving, the address has to change inside the py. Okay, but the garbage collector actually know how to do it. The thing is that py can exist only on the stack. The garbage collector then knows that there can be some local variables on the stack that are actually reference to things inside the JSA, and that these pointers are not necessarily at the start of the object, but can also be interior pointers. And when the GC moves objects around, it will go inside the stack and it will walk the stack and look at all the variables that are marked as by reference and just shift them to the new address if the object move. Okay, so the idea with the span is that it contains a byref at the beginning. So this is the PTR, and this byref can point to something inside some memory region on the length. So this way, if the memory region is moving due to the JSA moving object around, the pointer inside the span will be modified to point to the new address as expected. So this is interesting here because once we have span, we can point to memory region inside arrays and use them safely without pinning the array. So without going unsafe with pointer, etc., everything is managed inside the span. Okay, so this is kind of best of both worlds. At the same time, you can point to, if the pointer is referring to a memory region which is not managed by the GC, no problem, it will just not move. But if it's pointing to some data managed by the JSA, if the array or the memory region is moving, the span will be updated. Only constraint is that span can exist only on the stack, like byref variables. So this span has a special thing that it can only be on the stack. So one of the things I do, of course, for my my function to read my file is that after doing some things I will explain a bit after, I will have this function render frame, which takes the width and height we get from the beginning of the file. And then it will take the source, which is the bytes from the file, as a read-only span. So I don't have to know if it's native memory or if it's inside an array. So the caller can decide how to use it. On the screen, which is a span of pixel, same thing, I don't have to know where it comes from. Either I can use a native API and with a native memory for the screen, like working with OpenGL or something like that, or I can use a .NET library and put the pixels in the screen, or for testing it will be in an array. For testing it will be easier to have things in an array probably. On this way I can also work with libraries like ImageSharp or things like that, which are using managed memory. So with the same function I can use both and I don't need to care. But the thing at this point is that passing two parameters each time inside every function is quite costly, because these are structs, and if I pass these structs along my functions each time, the problem is that structs are by value, so it will not pass a reference, it will pass the whole value. Okay, so here I have a first span which is one pointer, 8 bytes, and length which is 4 bytes, but the whole thing is probably, I think, padded to 8 bytes, so it will be 16 bytes. So passing a span on the stack will copy probably something like 12 or 60 bytes each call, so it will not be very efficient. Of course, what I can do is pass a reference to the span, and this way I will just pass the address of the span on the stack to the next level. But still, I have two spans, one for the source and one for the screen, and it makes a lot of passing around and a lot of address to get. So what I would like is create a structure that contains both span, like I did here. Okay, so I create a structure with both span. So we can try to write it. I have here a scratchpad to do that. So we can do something like type, this is my context. And what I will do is have a source which is read only span of byte, and let the destination, which is the screen, is a span of int 16. This is my pixels. Okay, and when I try to do that, I have immediately an error, which is that it's not permitted because I cannot create a type which contains ByRefs. Okay, first thing, probably I should do a struct, and this way it will be maybe a bit better. It will be not a reference type, so it will not by default be on the heap. But the problem here again with my struct is that this struct can be also embedded in a type, a reference type, as a value, and it's not possible because these are ByRef types. So the way to say that no, it cannot be elsewhere than on the stack or in a register is to use this special attribute, which is IsByRefLike. So here it's in the system runtime compiler services. And when I do that, no, the code is okay. So what the IsByRefLike attribute says is that this is a structure which is ByRef, which contain ByRef, so it should be handled like ByRef types. And as ByRef type, they have restriction where they can be used. For instance, they can be used on the stack, maybe alias to registers, but they cannot be used by reference outside of the stack. So once I do that, the restriction is in place and the compiler is happy, I can create my structure. So I can show you here. This is here. My structure is IsByRefLike, like that, and I will be able to use it. So no, what can I do with that? The question is how I get this span and this read-only span. So here I'm using globally monogame. So monogame is providing me some array to write to for the file, for the screen. I can show you my window. So it's here. And my function is calling I will find it. So I get my texture, my sprites, and all that. And here, what I do is that the draw function is called, and I call my render function, and data is data from the texture, and this is a pixel array. And I will convert it to a memory. And memory is a type that is not IsByRefLike because it can either point to a table or to an array, or point to some native memory. But when it is an array, it will have a direct reference to the managed array as an array, and it can be used by reference. So here I create a memory object on my array so that I can use it. And the other part is where does my data from the files come from. And here for my data, I will just find it. Here it is. What I do is that I use a memory map file. So I don't know if you already use the memory map file. Memory map file is using the Windows or Linux virtual memory management to take a file and put it in memory like just a raw memory. So the content of the file will be accessed directly as a contiguous array of continuous memory array of bytes with the file inside, and we can use it. We can access it with a view accessor here. And what I did, because it's not yet available in .NET 6, this memory region give you access to a pointer, but does not give you a memory, which will give you access to a span. So I created my own memory management for that. And so to generate memory of T from unmanaged memory, you have to implement a class that is inheriting a memory manager like that. So here I implement memory manager with my view memory manager. I pass the memory map view accessor, and you just have to implement those three methods. So dispose, I just dispose the accessor, get span. And for the get span, it's a bit long and a bit complicated. I take my accessor, I call the safe memory map view handle, and I get the dangerous get handle like that. So I get a handle and I convert this handle to a native int. So now I have a pointer, and I convert to a void pointer, and then I create a span from it. And of course, my span, I must give it a length, and I give the accessor capacity. So of course, if you get this wrong, everything is becoming unsafe. So this is kind of code you don't want to write every day, but once it's written in a good way, no problem. Everybody can use it and play with it, and it will become safe. So here we have also to create pin, but it will not actually be pinning because the memory from the memory map view accessor will not move. So it will just do actually the same thing, get the dangerous, get the dangerous get handle to get the address, convert it to a native int, do the pointer arithmetic needed, and return a memory handle to that pointer. And after that, when you do that, you will just get a memory of t, which will give you slicing. So you can take a memory of t and slice it to smaller parts. And you can also use it with to get a span on the memory region, and then you can pass it to all our rendering. Okay, so this is a part. All the code will be available online. So if, of course, if you want it for reference, just go to my GitHub. I will put the address of my GitHub, but you can find it at a thing before coding. Okay, let's go.
We have a small,
yes.
We have a question from
Yes.
Vincent about the monogame stuff, asking if this is XLMish. So I think this.
If it's what? Elmish?
Yeah, XLMish is the library that does Elmish on monogame. So
no, it's just it's just a standard monogame library. And so I'm here for the nomemalloc presentation. I'm using the developer branch because there was previously some problem in with the memory allocation in monogame. Actually, it was allocating a closure in an inner function on each frame rendering. So all the code I was writing was not allocating memory, but this function call was actually, so the GC was still running. I tried with Nugget. So before that, I had a custom version of the library for my lead where it fixed that problem. The Nugget currently is still allocating this closure, but in the developer branch is working fine, so it should be okay today. The problem with the closure, because it's interesting for our nomemalloc topic, was that monogame is trying to render, to call the rendering function on its own thread. And so there is a function for the rendering, which is doing something like if is on the right thread, on the if is on the rendering thread, and in this case it will directly call the render function with the parameters, and else it was doing something like schedule on rendering thread with the lambda, which was actually doing the render with the parameters. And the problem with that is that even if we are always passing here, actually the capture here is allocated at the beginning of the function by the compiler. So the way to actually do this was to say render on thread with the parameters, and then put this with the capture here on in the render on thread function, and then this part is not allocating any capture, neither in the true case or in the else case. So no closure is actually allocated. So yes, this is things you have to monitor if you want to reduce allocation. Having things like that, even in case you don't, you never call, can allocate, and you have a hidden allocation here. So let's go back to our renderer. So the renderer now takes a header. So this is a structure, once again, that we could read at the beginning of the file. So let's go back to the beginning of the file. It's here. So I just take the file name, compute the path, I create my memory map file, I get an accessor, and I get a memory owner from it. And from this memory owner, I get the memory of T. So it's a memory of bytes here. This is contiguous region with the bytes of my file. And from here, I can access it in different ways. So here, what I do is that I take the span in the memory. And so I have this stack-only version of my memory region here, which point to the beginning and has a full length of the thing. And what I do is that I use Marshall read on the span to read the header. So I just describe my header in the structure like that. So I got all the size of the parts of the thing in the file I showed you here. So this is a file header. So as you can see, size, magic, frames, width, 8 flag speed, and we have the length in bytes of each part. And so in my program here, I just created a structure with the same layout. And after that, the reading is just using memory Marshall read. And here I have a copy with everything filled, okay? Then I'll read at these two offsets, which are also documented in the file. I read the two 32 bits Little Indian values, and I get 2 integers, okay? And then I can create my first view, which is actually slicing from the offset to and the length is size minus offset. So I reduce the size of my part. And the other view is using offset 2 in the same way. And I get 2 memory of parts that will contain my frames, okay? And now I can just call render with that. And that's all, okay? So,
before complete, we have a question from Alois about the closure allocation, asking
yes.
whether would there be a way to inline it somehow?
No, the problem with closure in .NET is that today they cannot be inline. Actually, something that could theoretically be done is that if .NET could know that the values in the closure will be used directly during the call and then not used anymore, it could allocate the closure on the stack, okay? But this analysis is totally not trivial, and it's called escape analysis to know if some variables escape the direct call tree and are stored in outside reference like objects on the heap and things like that that live longer. So if you know that the access to the data will not outlive the execution of the function you're calling, it would be theoretically possible to actually create the closure on the stack, and then it will not allocate. It will just use the stack. It will not.
Yes, I guess in this case,
yes.
it would not really be possible because you're starting a task with it, so there's no guarantee that it won't outlive.
So exactly, in this case, it's totally not possible. And inlining will not be possible also because you will have sometimes in between where the data should be somewhere, and somewhere in .NET means on the heap in this case. So I go back to my render function. And so the render function is just doing this. So I have several copies with several level of optimization. I will show the basic one, the most basic one. So I have a view, which is my bytes, and I have my memory pixels. This is my screen, and I just check if I'm at the end of my file, because I will shorten my byte view on each frame, and when it's empty, it's that I just reach the end of the file, and in this case, I will just start from the initial value, which is the initial view, and so this is here. If it's empty, I take my initial value back. Else, I just use the value of the parameter. And at the end, each time, what I do is that I take my current memory region and slice it by skipping frame size bytes. So it will get shorter over time. And when it's empty, we will just go back to the full view. Okay, so this is just my loop rendering this way. And after that, I will just call the render frame with the int from the width and the height from the header and the spans of my two memory region, and then it just span all the way down. Okay, but even if those things move because of the GC, which will not be the case here, it should still work. Okay, so here my render frame. What does it do? I have a width, I have a height, a source on the screen. I take my source and I interpret it as a frame header. So the frame header here is this structure with a size, a magic, a chunks, and a reserved bytes. And I take the size and I use it as the same as the frame size that will be used also to return to know how much bytes to skip at the end. The other thing is that I skip the frame header by moving past it. So I slice of the size of the frame header. And what I do is also that I create a slice which is just the frame size length. But since the frame size is including the frame header size, I remove it so that no, I just have the bytes after frame size after the header and with exactly the size. So this span contains exactly what I want. From that, I read the chunk type. So again, I read the chunk type from the chunk header, and the chunk header is containing a size on the type. Cool. And I get the type. So what are chunk types? You will tell me. And so in this video format, this is a very basic video format. You have frames. Frames can either contains can be either a full frame or be a delta frame. A full frame will contain chunks that either have a size and then the pixels directly in the file. Okay, not more complicated than that. The other type of chunk is fill chunk, and the way it will work. No, it's not the packet, but here, yes, it's the chunk type is either RLE, so run length encoding, or delta. So run length encoding is working like that. You have packets, and the packet can either contain a size on bytes, okay, and you just have to copy that bytes to the screen, or it can contain compacted pixels, and at that point you will have a number of pixels on one color, and then you have to duplicate this color, the number of pixels. Okay, it's not more than that, and then you get your image. And for the delta, it's just a bit more complicated because now you have three kind of operation. You can have either one of the previous, or you can also have indication to skip some pixels to keep the same value, the same pixels as the frame before. Okay, so just basic. So here what I do is that I create my structure with my two spans here, and I will pass it by reference, which is possible because it's on the stack, and so I will pass the reference to on the stack to the callee, and they will be able to use the values, but I'm just passing one pointer the function, which is making it a compact way to pass it without copy to the callee. And then I create two mutable variables, and I will pass these mutable variables, which will be updated inside the functions. So for instance, I'll show quickly the underlines. It will get the height, the context, and the two mutable variables, which are the index inside the source and the index inside the screen, which will be updated along the way. So here, for instance, I read the number of packets. I increment my source pointer index by 1, and then I call the render packets with the number of packets and the new values. Here, I do the same for the packets. I repeat for each packet. I read the size count, which is a value indicating both the number of pixels, but if it's a copy or a fill. And I increment the source index by 1. And then if it's negative, it means that it's a copy of pixels. So I just take the count by negating the value, and I copy the pixel to screen. Or in the other case, it was actually a fill. So I will fill with the same value, and I will fill the screen with the value. So these two functions, which are basically the same in the other version, I have my context, I have my source index, my screen index, and the size. I will just slice my source using the source index and the size multiplied by the size of pixels. So I have a memory region that contains all the pixels I want to copy. I slice my screen span at the screen index, iScreen index, and with the size. So I also have a memory region of the same size in the screen. And then I just convert my slice of bytes to a slice of pixels, and I copy it. So it will just be a memory blit, like take the memory, copy it there, and .NET does it very, very fast. So very, very quickly. And then I just have to increment my two indices, and we're done. For the fill, it's quite the same, except that I just read 2 bytes in my source at the source index to get the color. Then I create my slice for the screen, and I fill it with the color. And then I just increase my source of the size of 1 pixel and increase my destination of the number of pixels. Okay, so now you've seen basically almost all the code. The only difference here is for the delta image. We have a skip. So skip x is the number of pixels to skip, and you also sometimes have some number of lines to skip. So it's just adding this thing. So it's of no interest for the rest of the discussion. I will move quickly on that. This version is working nicely. I can show you. We will use this version. Here, I will make a version without the benchmark first, so that you see that it's working. Up, like that, and we run the code. And now we should see, yes, the animation here. Great. The other thing I did is that in my console, I have also implemented what is it called, an event listener for events coming from the garbage collector. So at some point, if JC triggers, we will have something printed here. So actually, I let this code run for multiple hours, and no JC triggered. As soon as you add 1 byte allocation, you're sure that it will trigger quickly. So we can let this code, and it's actually never triggering a JC, not JC0, not JC1. It's just running like that, okay? Because we are only using spans, structs, and all the memory has already been allocated and it can just run. So this is cool, this is working, but we can do better. We have still some minutes to do that. The problem I have is that
first we have a question from Sean asking if the offsets that you read from the file are outside the range of the file due to corruption or deliberate attack, what will happen? So this is
yeah, that's a good question. So each time I try to access the memory, I do it using spans methods like the index on the span. I can show it, for instance, I have one here. So here I'm trying to access the memory at this index, but by default, what .NET is doing is that it will actually raise an exception. We can try it like writing let access span, okay, and we will have a span s, which is a span of byte, okay. And what we will do is that we will put an index I, and we will try to write something inside. So s of I, and we will just put 0 inside. It's a byte, so I have to write it like that. And if we look on the right, this is the assembly generated by this code. So I'm using here FastMe. This is the .NET tool provided by DH to decompile F# to assembly language. So this is a GTID assembly, GTID by .NET runtime. And if you look at what's happening here, it's first reading the length and checking that the index we are trying to access is in range. And if not, it will just go here. And this is a call to raise an exception. Okay, so this is safe. The call with the value outside of the range will raise an exception, which is what we expect from the code. We can catch the exception upper in the stack, and it's safe. Okay. So you can ask what we gain from actually accessing the span. The thing is that the .NET runtime is actually quite efficient in optimizing some patterns. For instance, if I do this, like trying to initialize 2 bytes like that. Yes, I don't need the ice, this is why. What it will do, as you can see, it will first test that 0 is okay, and then test that 1 is okay. But if I reverse the access, the code will be shorter, because when I try to access the 1, it will fail. But if the 1 passes, it knows that it's okay to access 0. Okay, so there is just one check here. Same thing if I do something like if s.length is bigger than 2, then do that. Here I still have the check, but this is my check. Okay, this is not .NET check. It will here not do the actual check to verify that it's okay, because we already did it here. And .NET is able to optimize this kind of access. So when you start to be fluent with the thing, you can do access like that and reduce the number of instruction generated, the number of checks, the number of memory access. And it's I will show a bit more after that on the topic. So yeah, something was problematic with that is that for development and debugging, it's very cumbersome to pass these mutable variables, because the problem is that if I have a problem when I'm here and I want to see what happens, I have to go back. But the problem is that at this point, the value have changed. So the value have changed. I will have to remember what was the value to set them in the debugger to be able to replay the debugging. or my indices have already changed. I will not get the same value, and it will probably be a disaster. So what I wanted is to go back to more functional patterns. And so I created two different functional versions, but I will show a first one, which is this one. This one is actually a functional version of it. It will not mutate anything. So as you can see, my render frame, so the render function is the same. The render frame is actually calling render lines with values, and these values are not mutable. So my indices are just value passed to the function, and I will not mutate them. Okay, this is not mutable values. So how does it work? Let's see the render line. So the render lines here take the 8, the context, and the both indices. And what it do is that it says, okay, it's a recursive function. If the 8 is bigger than 0, it's not over. So I will call the renderLine function, which will render one line, get the new value for the source index on the screen index, and call the renderLine again with 1, the 8 minus 1, okay, and the new indices. So this is a recursive function that will just say, okay, we start with, for instance, 100 on I don't remember the number, 360 lines. It does the first lines, get the new values, and call itself again with 8 reduced, again and again until it reaches 0. And when it reaches 0, it just returns when we go back. So maybe you can find, yes, it's far less efficient than doing the actual thing, but in F#, actually the recursive function are quite efficient, like sum n and then an accumulator. This is a dumb function, but and then we can say that we'll do something like sum n minus 1. So we reduce the number and we add the accumulator plus 1. And if we do that, what is saying? Yes, this is a generic method because it's not returning. Yes, if n equals 0, then it will return the accumulator, else it will just call itself to increment, like that. And actually, if you look at the code, you can think, yes, it will do a lot of call to itself, but if you look at the code, it just takes that the value is not 0, else it just will return like that. No, if it's yes, if it's 0, it will return the accumulator, and if not, it will increment 1 on return and just jump. So I have no call actually in my function. It just implemented as a loop. So for me, okay, no, it's a recursive function, but actually it will be implemented as a loop. There will be no extra call. The renderLine function will do the same as before, takes the number of packets, call render packets. So here, again, it's a loop. So I create a recursive function. This function will call the render packets with my values, get a new value back, and then call itself again. So the problem here is that since I have two indices, first, it will use two registers or two places on the stack to pass the values. And then the problem is that when I want to return these values, I need some way to return both values at the same time. So we can use tuples in F# like this, but the problem with tuples is that they are basically allocated on the heap. So it will defeat all what we did until now, because it will allocate some memory to store the tuple. Hopefully, in F# we can use a struct tuple, and struct tuple is a tuple that will be passed by value. So in this case, return on the stack, and it will not allocate values. So as you can see here, I will return it, give the new names of the to the value inside the struct tuple and pass them. It's okay from a functional perspective, but performance-wise, the small problem is that I still have a lot of parameters. Know that value are not pointers, so I remove the dereferencing of the pointer in some way compared to before. But now I have to pass tuples as return value on the stack, and it's a bit more expensive than passing simple values. So all in all, it's quite equivalent. So the question is, how can we make it better?
So yeah, before we move to the next bit, we have a question from Darren. Yeah, but I'll maybe rephrase a bit. So yeah, the question is, when you have a recursive function like this,
yes.
Can you always trust that it will be optimized in the way that you showed, or do you have to check how it's optimized?
Yes, actually, the compile, there is no compiler warning yet, but it's a requested feature for F# for recursive tail recursive function. The only way to be sure today that it will be compiled like this is that you have to be tail recursive. So tail recursive is either it returns the value, your function either return a value or is returning the result of the call to itself. Okay, so here I call sum and I will return the value of sum without modification. Okay, in this case it will be safe. If I change this implementation, like doing something like value no, something like that. If it's 0, I return 0. And what I do is that I will do 1 plus call to sum -1. So it will return 0. But when it will do, when I will put 1, it will say, okay, I do 1 plus sum of 0. Okay, and then when I put 2, it will say it's 2 plus sum of 1, which is 1 plus sum of 0. And here, this is totally not the same because you have a call here, okay? So I use this accumulator here to make the function tail recursive. So it's important to be a bit confident with a tail recursive function. It's not very difficult to write. It's some thing to train a bit, and then you see exactly when it will do. Whatever, if you have function and you want to work on performance, I really advise you to look at the assembly generated, and this way you know. So okay. So the next point was passing two reference is costly, passing two values is costly because the .NET, the Windows conversion and that is used in, but it's almost the same for Linux. For using register to pass parameters to function is limited, if I remember correctly, to 3 or 4. And the problem here is that we have in most of our function a lot of values, okay, to pass. So they will be passed on the stack and it will be costly, okay, because instead of just having the value in a register and calling the function and the function can access it directly, you will have to prepare the stack, put things in the stack, and then use it. So I looked at this code and I was thinking, hey, by the way, this is two 32-bit integers, and there is no reason for this to be bigger than the int max value. Okay, so what I can do is that I can pack those values inside the 64-bit integer. Okay, so I could write all the code like pass both indices like an int 64 and then do all the arithmetics. But if I go this way, it will be very hard to read the code. So what I did instead is to create a struct, of course. So the idea is that type indices, and we will do a struct. And this struct will just contain a value which is the int64. Okay. And for instance, we have a member which is a value dot value equal value. Okay, like that. But after that, we can do something smarter, like a member member dot source, and it will be the source index. Okay, and what we do for that, we will just take the 32 lower bits of the value, and for the screen index, we will take the value, shift it by 32 bits, and then convert it to int32. Okay. So you will tell me, but it will be more expensive like that. But actually, if you look at the get value, it just move R6 like that, and the get here, this is straightforward, and here it's two instructions to actually extract the thing. So very interesting thing with structs like that, especially when you have a value which is a single native type, is that the struct disappear almost completely. We can also create a new constructor with the source and the screen value, which are integers, and we will just call indices with the int64 value. So we take the screen and shift it 32 on the left. I have to cast it to int64 before, and then make a OR with the conversion to int64 of the SRC value, like that. And it will just do the construction. So the constructor is here. That's cool. And now let's say that, for instance, we have a function, and this function want to use something like indices, which is indices of 2 and 4. And now we can look at the code. So I have to, yes, just do that. Where is my function f? No, it's doing nothing, so it will just return it. Yes, like that. And if you look, actually here, if you look at the code, it says, okay, take these two values, go through the constructor, shift them 32 bits left, and then do a OR with the other values, and then you construct the thing together. And the code is that return the value exactly what we wanted. There is no extra instruction. Okay, so even if I want to return, for instance, the screen part of this, it returns directly 4. And if I want to return the source part of it, it will return directly 2. So the inlining capability of the F# and or C# and the JIT is totally awesome. So of course, sometimes you want a bit more like this, but this is just 3 lines of assembly code. I mean, so this is just take the value, move it in the register, do a OR with the value 4 already shifted, and then return it. So it's very basic. So it's very, very fast. And the thing is that no, both indices can be passed in a single register, 2 functions. And with it, we have a clear performance gain. So I will show you quickly the version with the indices. This is this one. Yes. No, not this one. This is this one. So this is the value I showed you, the structure, source, screen, the value. I created 2 add source and add screen functions that create a new index with the value plus the other part and all that. so that it's easier to write, and it returns a new value. So it's an immutable structure, of course. But actually, the structure will not exist anywhere in the assembly. It will just be an 64 bytes integer that will be passed around. Okay, but I have this code that gives higher level representation. So what I do here is that I call my render lines with index 0. Both index have value 0. Okay, and then here I can do my recursive function, and I call render lines with my index, and I will get a new index and will pass it to the function back like that. Here, the render line is taking the source at the source index, okay, and I just call render packets with e, where I add 1 to the source index. Okay, but this is immutable. I never muted the I index. I just create a new version of index with the source incremented by 1, which is directly passed to the function here. And then here I have my index. I can check. I can do my recursive function. When my function here is finished, I return the index at the end of my computation. Okay. But here I can call render packets with that. And here, so I read 1 byte, I add 1 to source, I get my new index. And from here, I can either copy from here or fill from here. And the copy also is doing this. So it's taking the slice on the source at source index and the size expected, the screen at the screen index. So this is where the shift on the right will happen. I get my slice, I do the copy. And what I do then is to call the add, which will compute both the new source index on the screen index by adding size and size of pixel on the source and size on the screen. And it will return a single 64-bit integers that will be passed. So no need for accessing the stack to return the value, because I can just pass it as a 64-bit integers. So as you've seen, there are many techniques to avoid allocation. This version of the code using the compact index structure is quite fast. It's under one. Actually, this version with the compact integers is almost twice faster than the mutable version for the globally similar code. And it's, yes, totally twice faster than this version, which is totally mutable, but create more structures with more copy. I made some other variation, which is a compact mutable. The idea is that everything is immutable except that for loops, I did not use recursive function, but loop with a mutable variable. Okay, so instead of calling the function itself, it creates a mutable variable, and on each call, it will get the value back and put it in the mutable variable to be able to call a loop. Okay, but actually the performance is the same, and the code is not really clearer, and it's not easier to debug. So no performance gain here. So actually, the best version for now is the compact integer version. So I can show the result, which is actually the same. Here, like that. Yes, it's working. And to show the result here, I have I use a benching, so it will do 100 render of each frame each time for each frame, and then it will wait for 10,000 rendering to make an average of the timing. So we can see the time per frame here. So we should, so on the first call, there are still a few optimizations done by the sheet, so it will get even a bit better. Of course, my machine is also doing the streaming for Zoom, so the performance is are a bit less good than usual. Without Zoom running, I'm usually at 0.5, but here I have this version, and the version with the mutable I showed at the beginning is giving this thing. Three, two, one, up. Yes. So we can see that it's a bit higher. The difference is less visible due to the machine being used for the streaming. But anyway, if you test it in benchmark.net, you will see it more clearly on a clean machine, of course. The thing is that the code is more compact. It's still readable. It's totally immutable, so it makes the debugging easier, and it still makes totally no allocation. Okay. Are there any question on the topic here? No more questions.
We don't have questions waiting right now.
Okay. Yeah. So.
Vincent is asking, you still load all the file? Yeah.
What?
You still load all the file?
Yeah. Yes. The whole file is loaded from the memory map file at the beginning and mapped in memory. Of course, you could do differently depending on what if the size is several gigabytes. But actually, the concept of the memory. The memory map file is actually to let Windows manage which pages are in the memory or not by using the same system as what is done with virtual memory management. Actually, this is exactly the same structure. And I showed this on Windows, but it's working equally on Linux, of course. Yeah. So thank you for joining. Of course, if you have other questions, don't hesitate to contact me or us at DH. If you were interested, don't forget also to follow, to subscribe to the Meetup group, because we'll do more presentation, technical, less technical. Of course, we have a mix of all the thing we do at DH. And thank you again. Thank you, Loic, for the questions. And see you soon. Thank you.
Yeah.
Another question?
Oh, yeah, no, last time you're just asking, I didn't gain what's the final gain twice as fast? That's what you said.
Yes. And on the machine which is working for other things, it's less visible. But yes, I did a lot of benchmark prior to that, and yes, there is a real difference. And we use it. We use these things in production with benchmark done using benchmark.net, and we have very different results based on this implementation with compact int and using spans or not. Yes, clearly. So thank you.
Thank you.